Assalamualaikum, Prof.
Salam. Bismillahirrahmanirrahim. Assalamualaikum and good afternoon. Can you hear me?
Yes.
Yeah. Okay, so today I will continue chapter 2 by looking at chapter 2b. So I leave chapter 2a, the rest of the slides for you to do your own study. And today we are entering to the chapter 2b of the test 1 last week. Okay, not started yet marking, so I hope all are positive, inshallah. So for chapter 2b, I will discuss about correlation theory, analysis, and some applications. So there are two types of autocorrelations, which is type of correlations, which is known as autocorrelation function and cross correlation function. So correlation is very important in system ID because it will involve searching on the relationship between two different data, which is known as the input and the output as well. Okay, so in system ID, we have different input and different output. So that's why we are comparing the similarities between the output and the input. And for that particular, we have two types of correlation known as autocorrelation and cross correlations. Short form is ACF and CCF. So usually ACF is a graph of correlations which relate two versions of the same signals, meaning that we want to see the relationship between the signal and itself in the versus the time delay. Okay, so meaning that the output correlation, autocorrelation, the input autocorrelation. Okay, and then for CCF is a graph of correlation relating two different signals. Okay, must be two different, cannot be the same. If the same, it become autocorrelation. If different, it become cross correlation. Plotted again the amount of time shift between them. So that's why in particular, we describe ACF as for particular signals, while CCF is for the relationship between two different signals. So a non-deterministic signal, okay, cannot be defined by means of an explicit functions. For example, disturbance, noise, yeah? All the stochastic parts of the system ID is, we call it as a probabilistic manner. We cannot actually define properly, measure properly, okay, but it comes, go, and on. So when undertaking system ID, we the non-deterministic force functions and carrying out the analysis in the time domain is appropriate for us to use the statistical descriptions of the signals, which is known as the correlation functions. So in mathematics, we say that the correlation of two random variables in the expected value of their product shows whether one variable depends in any way or the other. So if we have a non-zero means, it's sometimes referred to the subtract the mean value before determining the correlations. And this is known as the covariance. So if you have two variables, values of a random signal at two different time instant, the expected value of the product depends on how rapidly the signal change at the time. Okay. So high correlations might be expected when two time instant are very close together. Okay, so the change between the signal A and signal B is very close, but much less correlation when the time instant are widely separated, mean far away. Thus, it has become appropriate for us to define correlation function or covariance function in which the independent variables is the time separation of two random signals. That's why we come out with the definition of autocorrelation and cross-correlation for a particular signal and two different signals. So the process of autocorrelation establishes the relationship between the signal and itself versus the time shifted. Okay, so we put a time delay -1, -2, -3, -4, and so on. When you're going to see the relationship between itself. And this is we call as autocorrelation function. And the value of the function is known as autocorrelation coefficient. Okay. So we can do it in hardware design and software design. If we are using hardware design, there is some signal generator, advanced signal analyzer can perform this, but it's a very expensive signal analyzer. I used to use this signal analyzer during my PhD study in 1990s. The product is from Hewlett-Packard. Okay, so this is kind of the schematic of the hardware, where you have one signal here, you sample the signals, and you tap the delay circuits, then you multiply. After you multiply, you average it, and then you plot it. Okay, all are using hardware like an oscilloscope, but we have to use the probe in order to tap the signal. Or you can buy from any product, for example, National Instruments. They also have this kind of function which can be interfaced to the computer for the correlator hardware. Or if you don't have the budget, so you have to use it mathematically, doing a computer programming. In MATLAB also they have these functions, okay, to perform the correlation between itself and between the two different signals. And usually we are referring to the mathematical equations here, okay, where the symbol here is phi xx tau. Phi is the meaning the symbol of the autocorrelation function. Xx meaning that it is the same signal that compare with itself. Tau is the time delay. Then limit t towards infinity. 1 cycle, 1 over t of the signals, samples. Integration from -t to t, xt is the signal, xt plus tau is the signal shifted by itself, multiplied together, and all are integrate with respect to dt. Okay, or this is on the positive side, or it can be on the negative side. Okay, because this function is symmetrical, so that's why you can do it on the positive side, you can do it on the negative side. So phi xx is the time average of the product of the value of the function tau, seconds apart, and tau is allowed to vary from 0 to some large value, maybe 100, maybe 200. Then the averaging being carried is over a long period of 2t. Okay, is a sample period that the period of the data capture that we apply. And the process is shown graphically, for example, in this picture. For example, you have the x tau, okay, xt. Okay, and then the signal itself shifted by time which is the time delay, tau. You can see that the signal is represented by the dotted line. So the dotted line and the solid line is the same signal. One is the original signal, the other one is shifted by time. And then when we do the autocorrelation functions, so you will get something like this, the graph. Okay, so the similarities of these two signals, the signal itself and the signal itself shifted by time is represented by the peak of the autocorrelation, which is known as the autocorrelation coefficients, which is over here, referred to the y-axis. Okay, so the area under shaded area is our concern in order to find the autocorrelation functions. So from the figure, it consists of operation of displacement. Okay, displacement means shifted. Okay, of the signal xt through a time tau, multiplication of xt by xt plus tau, integration of the product, and division by the integration time to give the value average of psi subscript x tau for a single value of tau. So this process will be repeated to other values to yield functions cxx tau versus tau. So you can see that SEF measure the predictability of the signals at some future time based on knowledge of the present value of the signals. So if the value tau second is closely dependent on the present value of the phi xx tau, it will generally be large in terms of the amplitude. So let us see a simple program, a rectangular pulse. Okay. So when we apply a computer program for the autocorrelation function, it will give you this kind of graph. Okay, this is a square. So when we apply autocorrelation for this rectangular pulse, it will give you a triangular pulse, which is the maximum is at the tau equal to 0. Okay, and then it goes down, and it will be below 0.1. Okay. Then when we sample this square wave, okay, meaning that we capture the integer data of this rectangular pulse. Okay, for example, we take this red point 1, 2, 3, 4, 5, 5, 5, 5, and 5 here. Okay, let's say we captured it on the integer data. Okay, the first signals, which is W, is 1, 1, 1, which is the amplitude, the voltage value. Okay, -1 is the second part of it. Okay, and then positive and negative. So we captured about 20 data. Okay, captured about 20 data, and then D is the W signal shifted to the time. Okay, shifted to the time, which is meaning that it's not shifted to the time. It is the duplicate of W, mean the same signal from the top. Okay. Right, so now at tau equal to 0, at time delay equal to 0, so we multiply 1, 1, 1, then we'll get positive 1. Negative minus by negative, so we will get positive 1. So total product of P is 20 from the beginning to the end. Then we divide by 20 because the length of data is 20, so the first coefficient of the autocorrelation will be 1. Then we shifted to tau equal to 1, tau equal to 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. Then at the end of the day, we will get the same thing again, which is equal to 1. Then we plot. Okay. So when you plot, you can see that it is a triangular. Okay. So this is tau equal to 1. So tau equal to 1 is here. Okay. Tau equal to 1 is here. Sorry, tau equal to 0 is here. Tau equal to 1 is here. 2, 3, 4, 5, 6, 7, 8, 9, and 10. So it repeated again and again because our signal rectangular pulse is the periodic signals. So it will repeat it again and again. Okay. and the maximum is equal to tau equal to 0. So for this purpose, I designed a program for you. Okay, so you can use it. You can generate any data from MATLAB. Okay, any random data, that will be fine. Then you apply this in the, you name the file as the data as u, and the y is equal to u as well, and then you will get the autocorrelation function, okay, using MATLAB. So this is some of the samples that I get from the book, okay, random noise, which is generated randomly, and the autocorrelation is maximum at tau equal to 0. Okay, for example, we do something, a simple program, okay. We need to use this because you will use this program in the assignment, which will be released in next week or next 2 weeks, okay. So we plot a random data y, okay, and then u is equal to y dot, y is equal to y dot, the same signals, okay. Then apply the kx score. Okay, so this is your signals, random signals, and this is your autocorrelation, which prove to be right at tau equal to 0 is the maximum value. So for sine wave is the, what do you call that, as a periodic signals. So we generate any values from 0 to 8 with the sampling time 0.02, okay? And then we generate a sine wave with amplitude 5, y5 sine x, and then we plot it, then we apply correlation function, autocorrelation function. The sine wave will be cosine wave, as shown in slide 35. So in a challenging problem, so we apply the sine wave here, deterministic signals, okay. F1, A sine omega t plus sine, a sine wave with the amplitude A, frequency omega, and phase psi, relative to the 0 time data mentioned in the next figure, which is here, right? So we're going to find the autocorrelation of the first figure, F1 A sine omega t plus psi. Okay, so what we do is we define it first. Yeah? We define it, sine omega t plus psi, multiplied by the same signal, A sine omega t plus psi, which is have the time delay tau. So this, since the signal is periodic, it is theoretically only necessary to average over one period, which is 2 pi over omega, where omega is the frequency in radian per seconds. So we enter 0 at the minimum integral, and then the maximum integral is 2 pi divided by omega. When we do the mathematical equations, simplified, so the integration can be carried out most conveniently by means of a change. So we, since to do the integration, the calculus here is quite complicated, so we replace u is equal to omega t plus sine. Then we differentiate it, and then psi is constant. So we apply it to the calculations, okay? So when you derive in slide 40, so you will get the autocorrelation of sine wave is cosine wave with the amplitude of A square divided by 2, okay? Cos omega tau, right? So the autocorrelation of sine is cosine. So for cosine wave, okay, so we do the simulation for cosine wave. So what will happen is, this is the simulation product of the cosine wave, right? So self-test refer to the example 1. So when you do the calculations of slide 43, you will get the cosine wave as well. So I leave it to you, slide 43, for you to try, okay, to find the autocorrelation function of the F1 is equal to A cos omega t plus psi. So for random binary signals, which is will be in the next chapter 2C. So we consider that the signal F2 has the general form in the shown of figure 3.5, which is here. This is random binary functions, okay? is a PRBS signal that always being used in linear system identifications, right? So what we'll do is the signal has a zero mean, two possible values, either positive and negative A, or positive and negative 1, or positive and negative 5 volt, and it's able to change from the one to the other every delta t seconds. So delta t second is the sampling time intervals, okay, from one here to another here, okay. Being equal probability of the signal is being positive A or minus A in each interval of delta t. So what is the autocorrelation function? So autocorrelation function is a triangular wave with the amplitude is square, and left and right is minus delta t. So since PRBS is a periodic signal, so the autocorrelation of PRBS will be repeated as well. Okay, so the PRBS shown in the top figure here is the 15-bit signals. So we can see that after 15 time delay is equal to 15, the autocorrelation will repeat again. Okay, similar to the left-right hand side here. So we have other function, random variable functions, which is shown here. Okay, so can see that the derivations here for white noise as well. Okay, so all are shown here, where white noise is a random signals or process with a flat power spectral density. So the signal contains equal power within a fixed bandwidth at any center of the frequency. So random noise, when we applied autocorrelation functions, okay, shown here. So the SEF of the white noise thus consists of an impulse of magnitude equal to the mean square value occurring at tau equal to 0 and 0 elsewhere, which is similar like a random signals that I shown before. So the properties of autocorrelations simply is listed here. One is even functions, okay. Psi xx tau is equal to psi xx minus tau, because the same set of product values is average regardless of the direction of translation in time. Then psi xx 0, when the autocorrelation is equal, tau is equal to 0, the mean square value or the average power of xt, that is the shown that the amplitude at tau is equal to 0 is the mean square value, or we call it as average power. On the third point, okay, the autocorrelation function at tau is equal to 0 is the largest value of the ACF. But if xt is periodic, then tau xx tau will have the same maximum value, but different time delay, okay, as an integer multiple of the period. So that you can see that when you apply on the rectangular pulse or sine pulse, you can see that not only at tau equals to 0 is the maximum, you can see that other value of tau will be maximum as well, because the signal is periodic. Then xt, if xt has a DC component, let's say a 5 volt or 10 volt or 1 volt, so you can see that the autocorrelation function also, has a DC component, which is the square of the mean value. So this is others as well. You can read by yourself, okay, the periodic component, the random component, okay, which is part of the properties of the autocorrelation function. So we go to the cross correlation function, which is comparing one signal with another by multiplications, corresponding instantaneous value, and taking the average. So the value of the function is known as coefficients, the CCF coefficients, against parametric time shift. So it measures the similarity between two different signals. So let's say you have a signal X and signal Y. Okay, so for system ID, you have a one input and one output, SI, SO. So you can compare it, find the similarities between these using these functions. It can be defined as mathematically, okay, shown here. Okay, it's about same like autocorrelation function, but you can see that the the notation is quite different. Psi, we maintain the psi, X and Y. So X is the first signal, Y is the second signal. Usually X is the input and Y is the output. Okay, and the rest is the same. Okay, Y, T plus tau, and YT, XT plus tau. Either Y or X, you shifted to the left or shifted to the right. So if you want to make a computer program, so you have to transfer this continuous signal to the discrete time, okay, where you can have a sequence here. So it's almost similar between the RXY tau above and RXY tau bottom here, okay. So we use this for the computer programming, okay, and then by shifting the time YT, okay, we can find a different results, okay. So we find the average as well for the X and Y in order to perform the CCF, and the cross correlation function have one important characteristic, which is symmetry between the positive tau and negative tau. And there is no particular significance when psi xy and psi yx is 0. Okay, generally CCF does not have a maximum value at tau equal to 0, not like autocorrelation function. Okay, so this is some of the examples to prove that the symmetrical and using the average value of the auto cross correlation function of two different signals. We have several methods of cross correlation. One is a point-to-point method, polarity method, evolution method, skip algorithm method, zero crossing algorithm, and frequency domain method. So let's say we have data here, which is 20 data, okay, of time, a square signal, and triangular signals. So we are correlating two different signals, which is the square and triangular. So this is the samples, okay? So you can see that each point is the samples. This is considered XX, and this is considered XY. Then we capture the data, integer data, for easy to apply in the teaching class, okay? So 1 multiplied by -5, you got -5. A is the X, the first signal, B is the second signal, it's different signal. A is square and B is a triangular, and P is the product. So you multiply between A and B at tau equal to 0, and then you divide by 20. Why? Because we average the product value by the length of data. So the first coefficient is -1. Then we shifted to the right at tau equal to 1, tau equal to 2, 3, 4, 5, 6, 7, 8, 9, and 10. Then we plot the value. You can see that the correlation, cross correlation function of rectangular and triangular will produce a sine wave. Okay, it's a sine wave. Right? So we prove it in using a computer program. Yes, it is a sine wave. Okay. So for that purpose, to do the programming, so we have algorithms. Okay, algorithm, or call it a flow chart, is a step-by-step logically how to calculate it until we get the value, the final value of the coefficient, and plotting the graph. This is one of the algorithms, okay, and some modified algorithm, okay, to make the calculation faster by using a different method, okay. And I attach here some computer programs for you to use it, okay, to apply. You generate a random signal U, you generate a random signal Y, and read the data as U and Y, and then you apply this program in order to find the cross correlation function. Same as autocorrelator, we have a hardware for schematic diagram. Okay, so you need a two comparator. One is input and the other one is the output. And this comparator will go to the shift register where one of the signal will be shifted. Okay, in these examples, input is not shifted, but output is being shifted. And then by being multiplied together, and after multiplied together, then will be averaged together and then plot. Okay, using the cross correlator. This is the dynamic signal analyzer that I mentioned to you. Okay, I don't have any idea what is the price currently. Okay, this is the signal analyzer that I used during 1990s during my PhD time. Is very helpful, very good instrument. Okay, for us to apply. Beside doing a computer programming for simulation, this one also can help you to verify and validate your results manually and simulation. Right, some question for you to try for slide 86, 87, and 88. Okay, and some answer applied in slide 89. Right, now we go to the next one, which is the chapter 2C. Okay, chapter 2C. Let me activate the chapter 2C. Okay, so this is a chapter 2C. Okay, the special signal that has been created as the test signal for the PRBS for the system ID. Okay, we know it is a pseudo random binary signals or PRBS generator. Okay, so PRBS generator is one of the important signals being used. Okay, in a system ID. Okay, probably is the most convenient input. Okay, compared to the square wave and impulse, because square wave, impulse, and sine is the pre-test. As I told you, is a pre-test before we test the signal in the, what do you call that, in the experiment in a linear system ID. So the SEF or PRBS that I discussed in chapter 2B provide the best and useful approximation to periodic white noise. So it's the most popular forcing function used in statistical system testing, and the general form of the PRBS is shown in the random binary function manner. So this is the PRBS 15-bit. We call it as a 15-bit pseudo random binary sequence, and the autocorrelation is triangular, repeated after 15 because the PRBS signal here is a 15-bit. So PRBS can take only two possible states. Okay, either A plus or plus A and minus A. This is referred to the voltage of that particular amplitude of the PRBS. So usually we set it as a +5 and -5. So the, what do you call that, peak to peak is about 10 volts. Okay, so PRBS state can change only at discrete intervals of time delta t, and the change occurs in the deterministic pseudo-random manner. So PRBS sequence is periodic with the period of t is equal to n delta t. Okay, so t is the period, n is the integer, and delta t is the sampling time. So it have properties. Okay, since it's a deterministic repeatable signals, it satisfies set of condition of randomness. First is the balance property. Okay, so if any period of the sequence of the number logic ones, positive A should be not differ from the number of logic zeros, which is minus A, not more than one. That is the balance property. And the run property is among the runs of 1, 2, 3, and etc. In the period half should be length 1, a quarter of length 2, and 8 length 3, and so on. And it should be as many of the each run of logic 1 as logic 0 state. And correlation property, the number of agreement and disagreement should not differ more than one. So this is PRBS condition, randomness that must be fulfilled in order to use this signal as the system ID tester. We have two types of PRBS signal, which is the QRC, quadratic residue code, and MLS, which is the maximum length sequence. So maximum length sequence is the most popular signal, okay, used in the PRBS, in the system ID. So length of PRBS is given by n is equal to 2n minus 1. So please remember this formula. N is equal to 2n minus 1, where n, small n is integer, and capital N is the maximum length sequence, or 15, 31, 63, and 127. Okay, so this can be generated by using hardware or by using software. If we are using hardware, so we are using a shift register, okay, where the first stage determined by the feedback of the appropriate modulo to sum. So it uses digital logic over here, which is known as XOR. Okay, you remember what is modulo to sum, or we call it as XOR? XOR meaning that exclusive OR, XOR. And this is the schematic of the PRBS, okay, where you have a 1, 2, 3, 4, 5, 6 shift register or flip-flops. And each of the shift register must be activated by clock pulse, okay, which have a interval of delta t seconds. Then we take two shift register together in the modulo 2 addition, so we call it XOR function. So XOR function is in the digital logic is the output is logic 0 if the input are different, and the output is logic 1. Sorry, the output is logic 0 if the inputs are different. The output is logic 1. Sorry, if the inputs are the same, the output is logic 0. If the inputs are different, the output is logic 1. So can you, what do you call that? Create the table. Okay, let's go to here. Let I do like this. Okay, X, Y, and then XOR. X, I will show you later. Okay, I create a table first. Okay, so 0, 0, 0, 1, 1, 0, 1, 1. So if the input is the same, the output is logic 0, 0, 1, 1, 0. Okay, I show you the table here. Can you see? Can you see, brother?
Yes, bro.
So we call it as a modulo to sum XOR function. Okay. So remember this. Please remember this, right? Same input, logic 0. Different input, logic 1. Okay. Because we are going to design the PRBS in a few minutes, right? So it's the binary additions, okay? And the shift register will be moved one stage to the right every delta t, every intervals, time interval. So this is some of the feedback, okay, being used in PRBI signals. If the shift register is equal to 2, so the maximum that we can generate is capital N is equal to 3 with feedback 1 XOR 2, okay? And N is equal to 3, N equal to 7, which is 1 XOR 3, okay? The correct stages until several's value. Okay, so this is the several's value that I get from the journals, okay, to generate the PRBS, which is the longest one. So in the class, we usually try to prove the simple one. Okay, let's say this one. It's quite simple for you to show in the class. Okay, this one, right? I think I can show you now how to create the PRBS. What do you call that? Maximum length sequence equal to 3. So design PRBS generator which produce maximum length sequence equal to 3, which is equal to n 2 power of n minus 1. So in this case, the small n is equal to 2. So that's why maximum length sequence n equal to 2 minus 1, which is equal to 3. Okay. Can you see here? I show you here. Sorry. Okay. So how to design it? First, we must have two shift register, SR1, SR2. Okay. Then you have a clock design. Okay. Clock pulse. Okay. And then according to the feedback for n equal to 2, n equal to 3, feedback configuration is 1 XOR 2, shift register 1 XOR shift register 2. Okay. Right. So this one, eh? So now we take this one, XOR 2, right? And the product will go to the shift register 1, right? And then the output will be anywhere from either shift register 1 or shift register 2. So I choose shift register 2 as the output, right? Okay. So this one is XOR. Right. So now we create a table. Okay. XOR. Okay. So we start with 1 first, logic 1. Okay, because clock pulse, when we on the switch, we make sure that every shift register is 1 first. Okay, so 1 1 1 XOR 1, sorry, 1 XOR 2. According to the rules here, 1 1 0, right? So it is 0. So 0 will go here, and this one shift to the right. Okay, 0 XOR 1, logic 1. Okay, then 1 will go here, 0 will shift to the right. 1 XOR 0, 1. Okay, and 1 will go here, 1 will shift here. Okay, 1 XOR 1, 0. Okay, now you see that After 3 bit, okay, this is 3 bit, 1, 2, 3, it will repeat again. See, it repeat again. Okay, so meaning that this is the characteristic of the PRBI signal. If this is 3 bits, 3 bit PRBS, okay, 3 bit PRBS. So you can see that when we plot the graph, so this is your clock pulse, okay, and this is your PRBS. So PRBS usually take one cycle of the clock pulse, okay. So the output is here. This is the output, okay. The output is from shift register 2, okay. Shift register 2 is here. So it start with 1, 1, okay. Then it goes to 1, 1 again. Then it goes to 0, okay, 0. Then it goes to 1 again, 1, 1, and it goes to 0, okay. So this is what I call a 3 bit, okay. This is one cycle, and this is the other cycles. Okay, so I want you to see again, okay. I will repeat again for the next one, the next examples, which is what do you call that? 7-bit PRBS. I will show after the break. Okay, so everybody stay tuned. We have a break for 10 minutes. Can we break 10 minutes? Hello?
Yes.
All right. Okay, 10 minutes break. So we come back 10 past 3. All right? Don't go anywhere.
Okay.
Shukran. Assalamualaikum. Can we continue? Hello.
Yes.
So we continue by designing the number 2. Okay. Number 2, 7-bit PRVS with a maximum length sequence n equal to 7. Okay. So design. So 7-bit. Okay. With 3 shift register. Okay. So if you look here, small n is equal to 3. Maximum length sequence is equal to capital N, 2 power of n minus 1, 2 power of 3 minus 1, 8, so 7. Okay. The feedback configurations is shift register 1 XOR shift register 3. Okay. So we design it as usual. We have a 3 shift register, 1, 2, 3. Okay, and each of it we will give a clock pulse. Okay. Okay, clock pulse. And then the feedback configuration will be 1 and 3. Okay. And then the output will go to the shift register 1. The output, so we can either choose SR1, SR2, or SR3. So usually practice, I take the last one. Okay, as the output. Okay. Clear? So as I told you before, the XOR functions SR1, SR2, 3, and this is the modulo. Okay. 0, 0, 0, 1, 1, 0. Okay. The concept is same input, 0, different 1. 0. Okay. So this is very important. And then you can construct the table. Right. So again, I do like this, easy for you to see. 3, then XOR. Okay. So the modulo 1, 3. Okay. So I use the blue one. So we activate all the shift register with logic 1 first. Okay. And then see, 1 XOR 3, 1 XOR 1. Okay, 1 XOR 1, 0. So you take the 0, go to here, the first shift register, okay? Because this is 1, this is 1. So the product is 1, it goes to the shift register, number 1. Then this one goes to the right, 1, 1. Okay. Then goes to the second stage, which is 0, 1. So 0, 1 is 1. Different input. So 1 will go here, 0 shift to the right, 1 shift to the right. Okay. So 1 XOR 1. Okay, 1 XOR 1, you will get 0. And 0 will go here, 1, 0. Okay, 0 XOR 0, 0. Okay, and 0 will go here, 0, 1. Okay, 0 XOR 1, 1. Okay, so 1 will go here, 1, 0, 0. 1 XOR 0 is equal to 1. 1, 1, 0, and then 1 XOR 1, 0 will go to 1. 1 is here, so 1, 1, 1. So this one will become 0. So this is bit number 1, bit number 2, bit number 3, bit number 4, bit number 5, bit number 6, and bit number 7. So bit number 7, after bit number 7,
Prof, may I
the
disturb?
excuse
May I
me.
interrupt? May I interrupt?
Sure. Yeah.
About the bit number 1, should we start with 111?
Yes, because
Is it necessary to start with 111?
because we have to activate like on the switch. So
On
it's
the switch,
bit 1.
okay. All right, noted.
So in terms of when we design the hardware, the LED is lighting. Okay, so the when the LED, the light emitting diode is lighting, meaning it's on, is a logic 1, logic 1 for all shift register. Okay, and then after 7 bit, okay, so it will repeat again, repeat again. This one, 1, 1, 0, 1, 0, 1, 0, and so on until the bit number 14. Okay, so in that case, so when we plot it, okay, so when we plot, okay, the LPR signal, so let's say we are using green color, okay, so this is your plot pulse, okay. I'm sorry, my hand drawing is not very good enough. Okay, so let's say this one is the 1 second. Okay. So this is the clock pulse, and then we see the output here. Okay, the output is at SR3. So we are referring to here, not the product. Okay, the safe register number 3, which is the 111. Okay, so is the logic 1, logic 1, logic 1, 1, 1, 1, 1. Okay, then it goes to 0, 1, 0. So 0, 1, 0, 0, 1, 0. And then it goes to 0, 1, 0, then 0, 1. 0, then it goes to 1 again. Okay, 0, 1. Okay, can see that this is bit number 1, 2, 3, 4, 5, 6, 7. So after bit number 7, the PRBS will repeat again. Okay, will repeat again, goes down, goes out, and so on. Okay, this is called a the period, which is T, is equal to N delta T. So in this case, N is the MLS, the maximum length sequence, which is this one, which is 7, right? So 7 multiplied, let's say delta T is equal to 1 millisecond. Okay, assume. Assume. So 1 millisecond, meaning that T, the period, is 7 milliseconds, right? 7 milliseconds. So every 7 milliseconds, first PRBS, second PRBS, third PRBS. Any question from the students? You want to ask any questions, or everybody is sleeping or doing something else? Any questions? Seems everybody understands, so we proceed the slide. Okay, so you can for the assignment, since we are on the what do you call that, online learning, so usually I ask the student to use the hardware, okay, and go to the lab, okay. But for this semester, all of you are very fortunate because we don't have lab anymore. Okay, we cannot attend to the university. We just study online. So we will going to use MATLAB in order to generate this waveform. Okay, using MATLAB and Simulink. I will give some examples for you, for those my past year students, how they apply this signal in MATLAB software. Okay, the important thing is you must have a MATLAB software. Right, so we continue. So as I told you before, on top of the hardware given here, okay, so I can say that for n equal to 4, okay, we have two type of feedback, 3, 4, and 1 form. So this is comma 1 XOR 4 also can, meaning that we have two options of feedback for MLS 15 bits PRBS, okay? And then oh, tak boleh. So kena padam. And then for maximum length sequence 31, 3, 5, and 2, 5. 3, 5, and 2, 5, meaning that this one, 2 XOR 5 also can. So we have a two option. Either you want to use 3 XOR 5 or 2 XOR 5. But in this case, you don't have options. This is mandatory. Mandatory mean you have to do the XOR in the bracket first. 2 XOR 3, get the value. 4 XOR 8, get the value. Then this product value will XOR this product value. Okay, so meaning that it is 3 times XOR, right? Okay, so for the details, you can refer to the slide number 15, which is from the journals, right? The second type of PRBS is known as the quadratic residue codes, QRC, which exists for n is equal to 4k minus 1 bit sequence, where k is an integer and n is a prime number. For example, n is 11, 19, 23, 31 is a prime number. The number is cannot divide by other number except itself. Okay, so QRC are difficult to generate using a logic circuitry, but the sequence can be pre-computed and read from paper tape for slow applications. And QRC advantage is that the successive sequence lengths are much closer together. Okay, on top of the disadvantage, it also has some advantage. So as I told you before, this one is the maximum length sequence generation that I show you. You can use the one that I explained before break, and after the break is something like this. Okay, we are using XOR equations in order to generate the maximum length sequence. So previously I generate maximum length sequence equal to 7, okay, in the using the iPad as the whiteboard, right? So it's similar, the same. You can see that after 7, it will repeat again, right? The logic will repeat again. You can see from here. Okay, you can see that 1, 1, 1, shift register 1, shift register 2, shift register 3. And this one is the product of the 1 XOR 3. So from the table, state 8, which is equal to state 1, length is equal to 7, then the sequence repeat, okay, as a PRBS waveform that I just drew to you just now. So now we will use the longer one, which is the maximum length sequence is equal to 15. Okay, so design PRBS 15 bits. Okay, maximum length sequence is equal to 15. Okay, so we have two options, which is either 3 XOR 4 feedback configuration, 3 XOR 4, or 1 XOR 4. Okay. So I'll show you here. So n is equal to 4 is the number of shift register. Okay, so you have 4. So CP, clock pulse. Okay, so 3 XOR 4 is here, right? Then it goes to here, and 4 is the output. Okay. So what next? Next is the table. Okay. So the table. So it's quite long. So you have to do it slowly. So S1, S2, S3, S4, and S3, XOR, S4, right? So we activate everything with 1 first. Okay, or maybe I use blue pen. Okay, 1, 1, 1. So 1, 1, 0, same input. Right. 0, product, and shift to the right. Okay, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. So it's become longer because the bit is longer, right? So I use a red pen, easy to see. So 0, 1, sorry, 1, 1, 1, 1 will be a 0. So 0, 0, 1, 1. 3 XO 4, 1, 1 will be a 0, 0, 0, 0, 1. 0, 1 will be 1, 1, 0, 0, 0. 0, 0 will be 0, 0, 1, 0, 0. 0, 0 will be 0, 0 will be 0. 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 0. 0, 0 will be 0, 0, 1, 1, 0. 1, 0 will be 1, 1, 1, 0, 1, 1. 1, 1 will be 0, 0, 1, 0, 1. This one will be 1, 1, 0, 1, 0. 1, 0 will be 1, 1, 1, 0, 1. 0, 1 will be 1, 1, 1, 1, 0. 1, 0 will be 1, 1, 1, 1, 1. This one 1, 1, 1, 1, 1. Right. So you calculate a bit. 10, 11, 12, 13, 14, 15. After 15 bit, it will repeat again. See, 1, 1 and 1, 1. Okay, so this is for 3 XO4. But there is another option, as I told you before. We can use this one or this one, or even we can verify. Okay, we verify. 1 XO4. Okay, so let us see. Okay, and practice together. You can use your A4 paper in order to practice. Okay, so what I did is S1, S2, S1, S4, S4. Okay, so have a long table. So, 5, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right? So we begin with all one LED light up for all shift register. Okay, so 1 XO1, same 0, 1, 1, 1. 0 XO1, 1, 0 XO4, 1, 1, 1. 1 XO1, so it becomes 0, 0, 1, 0, 1. 1 XO0 equal to 1, 1, 0, 1, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1, 1, 0, 1, 0 is equal to 1, 1, 1, 1, 1. Right. Now we have the repetitions at 16 bit. Okay. This is 1. This is 15. So you repeat again after 15 bit, meaning that the feedback configuration is correct. Okay, either 3, 4 or 1, 4. Okay, so in these illustrations, we see that the arrangement is different from the one that I explained in the whiteboard. Okay, so they have a stage 1, 2, 3, and 4, meaning that is the shift register. And we will show here. This is a shift bit 1, 2, 3, and this is 15. Okay, so 16 is repeating. Okay, repeating, same as the shift register one. Okay. So verify your answer in example 2 using a 4-digit shift register 1x4. I already show you the verifications. Okay, in the whiteboard. So what is your observation? It's the same. After 15 bits, signal is repeat again. Okay, so this is 1x4, so you can see that after 15 bits, it repeat again. Okay. 1x4. The previous one is 3x4. So what happened if we choose the wrong feedback? For example, 2x4. What will happen? Okay, and then your observations, you can see that it will not produce the maximum length sequence, definitely. Okay, so this is your bit number 1, 2, 3, 4, 5, 6, and 7. You can see that after bit number 6 at bit 7, so it will repeat again the stage 1. So this is not equal to the end value, the maximum value that we define, which is equal to 15. So this is a wrong configurations or wrong feedback that cannot produce the maximum length sequence that we want. Okay, so investigate the 3 properties of the randomness when we are using a 15-bit sequence. So we have a balance property, we have a run property, and we have a correlation property. So you can see that the balance property, we are referring to the number of ones and the number of zeros, okay, at the output. So let's go to the whiteboard just now. Okay, so you can see here how many zeros. 1, 2, 3, 4, 5, 6, 7. Zeros is 7. Number 1 is 1, 2, 3, 4, 5, 6, 7, 8. Logic 1 is 8. Okay. So from there, so from there, you see the number of 1 is 8, number of zeros is 7, so the difference is 1. So it fulfills the balance property of the randomness of the PRBS. And then for run property, the definition is among the runs of 1, 2, 3, etc. in the period half should be of length 1, a quarter of length 2, and 8 of length 3. And there should be as many of each run of logic 1 as logic 0 state. So when we take a length rank of 1, number of runs is 4. 4 divided by 8 is half. For length run of 2, 2 divided by 8 is 1 quarter. 3, which is number of runs is 1, is 1 over 8. And then length of run 4 is 1 over 8 is 1 over 16, which is fulfill the run properties. And for the correlation property is a matter of agreement and disagreement. Okay, number of disagreements 0 is 7, number of disagreements is 8. So the difference is 1, it fulfill the correlation property. So in this case, you can see that 1x44 will give the correct maximum length sequence, same as 3x44. Okay, so I give you, this is a sample of assignments, okay, done by the students, which is will be your assignment as well. Is the feedback PRBS 63-bit design. So it's quite long. The one that I discussed is 15. Okay, so this student designed a PRBS 63-bit design, meaning that the capital N is 63, the MLS, and the small n is equal to 6, meaning that 6 shift register, and the configuration is 5 XOR 6, right? Or 1 XOR 6, either one. So both will do. So first they are using a Simulink JK flip-flop. Okay, so you can try this at home. And then they put a scope, and then they put a clock pulse, sorry, to the converter, and will be inject to the each flip-flop. Okay, and then they simulate the circuits, the hardware circuits. Okay, using a Proteus. Okay, there are a lot of software you can use to design your hardware. And then they applied amplitude varying circuit design at the end of the PRBS signals, so that they can vary the amplitude of the output, okay, from 0 to maybe 10 or 5 volts. Then they simulate using the one that I draw in the iPad, okay. So 63, meaning that you have a 63-bit. So until 64. The logic will repeat again between 1 and 64 after 63. And then they implement in the hardware. So I usually for full-time student, and I will when during a face-to-face class, so I advise them to design this. Okay, I don't have any idea how you can do this during online learning. Okay, but if you wish to do this, you are welcome. Okay, you are welcome. I'm happy if you can do this design for me. Okay. And then they simulate in the Simulink MATLAB, okay, the PRBS output. And then they do some analysis for it, okay. So the one important figure for PRBS is the power spectral density, okay. We call it as a PSD, okay, where first we consider the value of tau is equal to K delta T, where K is the integer, and let the values of the sequence for intervals delta t to be x1, x2, x3, and so on. Then we apply the autocorrelation function for this mathematical in chapter 2b into the PRBS signals. Okay, so you can see that can be shown that the autocorrelations for PRBS is shown in figure 715 here. Okay, so you can see that the period is n delta t from tau equal to 0 to tau equal to 15, and the amplitude is E square, okay, which is the amplitude of the PRBS, okay, positive A and negative A. Then we will apply a power spectrum density formula. You can see that produce a bell shape here, okay, which is known as a sinc function, right? And it cut at 2 pi delta t and 4 pi delta t. So this is the first cut off of the PRBS PSD, power spectrum density, and this one is the second one. And this one is the 3 dB is the bandwidth of the PRBS, which is 2 pi equal to delta t. Okay. Okay, so the SCF is a periodic white noise. Okay, this is for the autocorrelation of the periodic white noise, and this is the autocorrelation of the PRBS and the power spectrum density, which is square and sinc function. So the power spectrum density of PRBS is shown in figure 715, differs from figure 7.8 in one respect, because one is a line spectrum, the other one is a non-continuous spectrum. So this occurs because the lowest frequency component in the PRBS signal is that corresponding to the period 2 pi n divided by n delta t. Okay, and all other frequencies are present as integer multiples of this value. So advantage of PRBS and practical consideration. So there is a lot of advantage. The first one is the binary nature of the signals of PRBS simplify the cross correlation calculation. Okay, so is to make the calculation easy. So we use a PRBS, okay, for the multiplication. And then the binary signal is easy to generate either using hardware or using the software. The important thing is the delta t, okay. Delta t is very important to choose the correct one, the appropriate one to avoid distortions. And then a PRBS signal's intensity is low, while with energy spread over a wide frequency range, so it's suitable for forcing functions. And the power of noise can be arranged to be in the band of frequency of interest by appropriate choosing the delta t and n. So the tips is choose delta t smaller than the time constant, and choose n delta t is bigger than the settling time in order to find the appropriate choice of delta t intervals, sampling intervals, and the maximum length sequence. So input of autocorrelation function is calculated to its fully accuracy by correlation over one period. Hence, to average out the effects of a system noise, the cross correlation should be carried out for an integral number of input sequence. That's why the smaller or the PRBS amplitude relative to the system noise, the longer the averaging time is required. So usually we use about 10 repeatable, what do you call that, cycles, okay, 10 or 15 cycles, samples of the PRBS in order to get the mathematical model. And to ensure that, okay, so the PRBS input has a flat power spectrum over the system frequency range. So we choose the amplitude plus minus A PRBS signal should be as large as possible without driving the process to be a nonlinear. Okay, and then delta t must be approximately 1/5 to 1/10 of the fastest process time constant. And then T equal to N delta T should be just greater than the system settling time. So these three is very important choice of PRBS parameter in order to get the important data during the input and output capture. So right, we continue with the illustrative examples here. Okay, we have a block diagram. Okay, being identified. So this is the unknown model, and then this is the PRBS signals. Okay, we inject over here, and then we have a DC level here, U of T. Okay, in order to support the amplitude of the TS-PRBS, and we have disturbance signals here, the noise signals. Okay, stochastic part, and then this is the output. Okay, right. So system under test is a second order system. It's not a black box problem, it's a gray box problem. And it is known as a second order system in the presence of noise. Okay, so you can go here, second order system, presence of noise. Forcing function is PRBS signals. Okay. The omega n value is 6 radian per second. The damping ratio is 0.3, meaning that the system under test is behave like under damped response. And the block diagram is shown in the figure just now. Excuse me. So in the absence of noise, the system can be subjected to an input change in the form of step or impulse function. Okay, so we assume first there is no noise. Okay, and then we inject the system with the step or impulse function, right? So figure 717 shows the response curve for a step magnitude and the impulse of magnitude 0.25. Okay. Right, this one, right? So you have an impulse response and you have a unit step response, right? The impulse response delta is 0.25. And from here, you try to investigate the value and estimate the value of omega n and zeta based on the pre-test of the system assumed without noise, okay? So you can see that the left one is the standard curve for the second order time response for step signals. The right one is the standard second order impulse response. Okay. So by comparing, okay, these signals, the step and impulse response that we get with the standard curve, so we get the value of the zeta omega n, which is equal to 6 radian per second, and zeta 0.3. Okay, zeta 0.3 and the omega n is equal to 6 radian per second. So we inject a 63-bit PRBS, the one that we designed in the hardware in the previous slides, with the interval delta t 0.1 second. So this is the sampling time. 0.1 second is about 100 millisecond. It's used as an input excitation for the system ID. Then the PRBS shown in the next figure, which is this one, right? So this is the input. Okay. This is the input. And this is the output. Okay. Without noise. Okay. Output without noise. A is the force PRBS, force function without noise. B is the PRBS signal this one B is the presence with noise, okay, and C is the false PRBS in the presence of noise, right? B is without PRBS. So B meaning B is the noise, okay. A is the output, the top one is the PRBS signal, 63 bit. Figure A is the PRBS with the absence of noise. Figure B is the noise, okay, the noise that enter to the system, right? Where is it? So you have to refer to the block diagram just now. This one, okay, disturbance signals, right? This is the PRBS signals, right? And then this PRBS will mix together, okay, combine together, become a PRBS with noise, right? So you can see that the noise is quite significant, okay, compared to the original value of PRBS. So the bit interval and the maximum length sequence can be chosen on the basis of preliminary estimate of the order of the magnitude of the dominant roots of the system. So confirmation through inspection of the correlation functions. So in the presence of noise, we can see that the system output comparison method with the standard curve is not suitable. So therefore, statistical testing can yield an impulse response curve with a minimum disturbance to the system. So the next figure shows the typical sample trace of the output response of the system in the presence of noise for a nominally constant input. So show here 7.8C show the response of the system to the PRBS in the presence of noise. You can see that when there is noise come, so we cannot do the comparison with the standard curve of step and the impulse, okay? So we have to do another method, which is using a correlation, okay? So figure 19 shows the autocorrelation of the input and output signals from the block diagram system being identified. So we apply autocorrelation of the input and autocorrelation of the output with and without noise. So this is the best method compared to the comparison with the standard curve of step and impulse. You can see that the ACF of PRBS signals is represented by psi XX. Psi YY is the autocorrelations of the PRBS, absent of noise, and psi YYT adalah noise system forced by the PRBS input. Okay, so all show the methods results is agree with the theory that we explained in chapter 2B. So we go to the real example, okay? Sorry, the correlation curve shown before was carried out of time duration of 130 seconds. Okay, this experiment, 130 seconds. So it's about 2 minutes, 10 seconds, okay? Which correspond to 20 period of PRBS, 63 bit. So 63 bit, 20 times, 63, 63, 63 until 20. Okay? 20 times 20 period of 63 bit PRBS. A longer period of correlation will have to smooth the curve. So the longer the data, the better, okay? Because we will smooth the curve and it provide the dynamic characteristic of the system being tested in the longer time span involved. So we can see that when we apply the cross correlation between the input and output, okay, we will obtain something like this, okay? Is a decaying sine wave, okay? I can say that it's a decaying sine wave, start from 0.1, it goes up, goes down, and it will settle down after about 2 to 3 seconds, okay? So you can see that without noise and with noise, it don't change too much, okay? There's no much change in the output of the correlations and the noise system as well. So you can see that the power spectral density for the input and output signals plotted in the logarithmic scale is shown here. So you can see that it goes up. This is the magnitude curve, okay? and the slope is about minus 40 decibel per decade. Okay, and then the shape of it is similar to the second order system power spectral density. Okay, so we plot the Bode plot. Okay, so this is the Bode plot. This is the magnitude. Okay, is a minus 40 decibel per decade, and the phase is start from 0, and at the end of the measurement is settled at minus 180 degrees, meaning that this is system has no delay. Okay. Example. So examples, can we see how long is it? Okay, not much. So examples here. A control system element was tested by the cross correlation method using a PRBS input of a sequence length 127 bits. Okay, so 127 bits is how much? MLS 127. Okay, and then the bit intervals is delta t 0.02 seconds or 20 milliseconds, and the level is plus minus 2 volts. So plus logic 1 is positive 2 volt and logic 0 is minus 2 volt. So the resulting of input cross correlation is plotted in the figure here. Okay, so what is the number of shift register that we need in order to produce the maximum length sequence 127? So n is equal to 7, small n, which produce n 2 power of n minus 1, 2 power of 7 minus 1, which is equal to 127. Okay, so the feedback will be feedback configuration SR4 XOR SR7. Okay, obtain the transfer function of the system. So we have to obtain a mathematical model from these correlations, autocorrelate cross correlation graph. We can see two graphs here. One is corrected for 0. The other one is uncorrected for 0. Okay. So by inspection, response appears to be a decaying sine wave. That is the important thing. Okay, the theory says that cross correlation for second order system will produce a decaying sine wave. So the cross correlation settled at a value of minus 0.064, which is here. Yeah. Minus 0.064, which is over there, all right? So in order to start from 0, okay, because the data that we obtain is start from minus 0.064, so we have to do some adjustment. Okay, so this is 0, this is 0.0164, right? So we have to bring the uncorrected to the corrected graph. Okay, we shift up. Okay, we shift it up so that it will start from 0. So we shift about 0.064. Sorry, 0.064. So we add 0.064 to all readings, resulting in the corrected graph. Okay, so the corrected graph has 0 crossing at 0.77 and 1.52, which is here. Okay, right? So giving two almost equal half cycles, which is averaging about 0.76 seconds. 0.77 plus 1.52 divided by 2, 0.76 seconds. So result indication is a decaying sine wave. So the equation that can fit to decaying sine wave is given by expression C exponent minus 80 sine omega t can be fitted to the curve. Okay. So the transfer function determination, so cycle time is 2 pi divided by omega, where 1.52 is equal to 2 pi divided by omega. Omega is equal to 4.13 radian per second. So quantity A, which is here, the power of exponent minus 80, okay, is found from the delay between successive peaks, which is 0.76 seconds. The height of the first positive peak is 0.405, and the depth of the first negative peak is minus 0.04. So that's why we take the ratio and equal to the exponent. Okay, so we apply natural logarithm. This is a natural logarithm. Okay, log base e. Okay, then cancel negative, then e is equal to 3.05. So value of c from these equations, okay, c, the coefficient of the exponent, can be found from the value of the cross correlation halfway across the first half cycle, which occurred at t 0.38 seconds, which correspond to the correlation coefficient of equal to 0.32. Equal it with the equation, so we get c is equal to 1.02. So to fit, after fitted an expression to the curve, we can find that the system impulse response to an impulse of strength times the bit interval of the PRBS, which evaluate as 2 power of 2 multiplied by 0.02, which is equal to 0.08 units. And the response to a unit impulse is therefore 1 divided by 0.08, which will be previous expression 12.75 exponent minus 3.05t sine 4.13t. And this, when we apply a Laplace transform, okay, so it will become 52.7 s squared 6.1 s plus 26.4, which is the second order equation under damped mode. Okay. So we verified using MATLAB. Okay, we obtain the decaying sine wave. Okay, as equal to the graph given here, the difference. Right. So some exercise for you to try at home. Okay. So we stop here 4:07. Okay, for the lecture number 6. So next week there is no class next week. Is a semester break. So enjoy your holiday, and we will see you again in 2 weeks' time. All right. Hello. Okay.
Yes, Prof.
Okay.
Yes, sir.
See you in 2 weeks' time.
Thank you.